Hello everyone, this is Greg Stitt from the University of Florida, and in this presentation I'm going to be giving you an overview of some of the research we're doing called elastic computing. So this should not be confused with Amazon's Elastic Compute Cloud. That is a completely different technology with a similar name. Our elastic computing basically deals with optimizing applications for what we call multi-core heterogeneous systems, which is basically any kind of system that has, multiple microprocessors and GPUs and FPGAs and other types of accelerator devices. So just to give you some background, there's been two recent architectural trends that have been getting a lot of attention. The first is an increased focus on parallelism. This is commonly seen in devices like multi-core processors. And there's also been a trend towards increased heterogeneity. So devices like graphics processing units and field programmable gate arrays are now more commonly being used in combination with a microprocessor to accelerate portions of an application. Now the reason these multi-core heterogeneous systems have been receiving so much attention is because they can provide very good performance and very good energy consumption. The problem, however, is that these types of architectures also have significantly higher application design complexity than traditional architectures. So it's no longer possible for a designer to rely on compilers and rapidly increasing clock frequencies in order to hide architectural complexity. So with these current architectures, designers have to have some low-level device expertise in order to explicitly take advantage of all of the resources. And while this is okay for certain designers, it's unrealistic for many mainstream designers to become experts in every type of acceleration technology that may exist. One example of this is domain scientists. So people performing computational biology, physics, chemistry. So these types of designers, they have some, basic knowledge of how to write C code or Java code or maybe some MPI experience, but they certainly can't create a custom circuit for an FPGA. They may be able to write some CUDA, but it's not going to be as efficient as a GPU expert. And yet these designers are working with applications that are performance critical applications. So this is a significant problem. So to address this problem, we've introduced this technology of elastic computing, which is basically an optimization framework that allows designers to specify what their application is supposed to do without having to specify how. And the ultimate goal that we're trying to achieve is to enable these mainstream designers, these people who aren't device experts, to effectively take advantage of the performance and energy advantages of multi-core heterogeneous systems. So before I start talking about what elastic computing is, I first want to talk about, what are the sources of this application design complexity so that you can understand the problems that we're trying to solve with this research. So the first problem, or the first source of complexity, is the fact that implementations for specialized accelerator devices generally require low-level device expertise. For example, if you're, using a GPU, you likely have to consider the number of processing elements or the particular characteristics of the memory hierarchy or the compute capability. There's a large number of issues that you have to take into account to create a highly efficient implementation. For an FPGA, it gets even worse. You often have to create a custom circuit for your application using register transfer level code, which is a very difficult process. The good news is that although this is a big problem currently, there's a huge amount of compiler research and high-level synthesis research that will help with this problem. And all of that research is complementary to elastic computing, so any improvement in compilers or synthesis tools will also improve and help out with elastic computing. However, there is a second problem that compilers, even with a perfect compiler and a perfect synthesis tool, there would still be a problem with complexity. And that problem is that different architectures require significantly different algorithms for executing efficiently. So in other words, there's no optimal algorithm for all architectures, for all numbers of resources, for all types of resources. Just to give you a simple example, let's consider just a simple application that's doing sorting. So if we were to, run this on a just a single microprocessor, we would likely want to use something like a quicksort algorithm, which would give us good performance. Now, if we were targeting an FPGA or a GPU, we would likely use something like a bitonic sort to get the best performance. So the problem here is that compilers can't convert between algorithms. So they have to work with the specification that's given in the high-level code, which is a single algorithm. And the problem with that is, although a compiler can compile any algorithm to any architecture, using an inappropriate algorithm for a given resource can perform very poorly. So this ends up being a huge source of complexity for designers, because it basically means that designers have to be familiar with a whole bunch of different algorithms for every problem and how those algorithms behave on different devices. It's a very complicated problem. And it gets even worse when you recognize the fact that there's not just this dependence between an algorithm and an architecture. Input size also comes into play. So for different input sizes, there may be, different optimal algorithms. For different data characteristics, there may be, better algorithms. For example, for sorting, if you have mostly sorted data, insertion sort may work better than other sorting algorithms. And so it's a huge source of complexity because the designer now has to be aware of all of these issues. So the way that elastic computing addresses these problems is by, instead of having a designer specify a specific implementation, whenever possible, the designer would call what we call an elastic function that's provided from some large function library. However, unlike a normal function library where each function has a single implementation, what makes an elastic function special is that we've basically taken the information that would be available to an expert designer, and we provide that as a knowledge base of different implementations, different algorithms, different parallelization strategies, different optimizations, different work partitionings for that corresponding function. And what that enables then is, when the application calls that function at runtime, the elastic computing framework then can explore that huge knowledge base to find a highly optimized implementation for whatever the current available resources are, whatever the current input size is, and potentially any other runtime condition. So just to give you a specific example, so let's stick with an application that's going to call a sort function. So at runtime, this sort function is going to be called, and it's going to invoke the elastic computing framework, which will then consult its knowledge base of information. It'll see, okay, there's one CPU available right now. So for a CPU, I know that a quicksort is the best performing implementation or the best performing algorithm, and so I'm going to execute this sort function as a quicksort. Alternatively, if we have, if an FPGA was our only available resource, when this sorting function was called, the elastic computing framework would see that, okay, in this situation, a bitonic sort is more efficient, and so I'm going to execute the sort using a bitonic sort algorithm. So one of the big advantages of elastic computing is that when there are multiple resources available, elastic computing can dynamically parallelize a function across all of those resources, assuming that there are benefits in doing so. So the way this works is that as part of the knowledge base of every elastic function, there's a set of parallelization options. And one common parallelization strategy is divide and conquer, where you partition a set of data into multiple subsets and then operate on those subsets in parallel. So an example of this applies to sorting. So let's extend the previous example to a situation where we now have both a CPU and an FPGA available, in which case, when the sort function is called by the application, the elastic computing framework is now going to partition the input into two sets so that we have two parallel sorts, one for each available resource. It's then going to select an appropriate implementation for each resource. So it's going to do a quick sort on the CPU, a bitonic sort on the FPGA. And in addition, it's going to find an effective partitioning of the input to keep each resource, to keep the computation load balanced between the resources. So it may provide 90% of the inputs to the FPGA and 10% of the inputs to the CPU in order to maximize speed up. And what makes this really effective is that this divide and conquer strategy Well, elastic computing can apply this recursively to basically support an arbitrary number of parallel resources. So if we have 4 CPUs and 2 FPGAs, elastic computing could simply partition the input data more times to create more parallel sorts. Or if we had 100 resources available, it could partition the input into 100 parallel sorts. And again, it does so at each step with the goal of load balancing all the computation to maximize speed up. So to summarize the advantages of elastic computing, first of all, it is a transparent form of optimization because from the point of view of a designer or from an application, elastic computing looks just like any other function library, except kind of behind the scenes, there's this framework that automatically optimizes each function call. It's also portable because without any changes at all to the application code, the elastic computing framework can optimize that code onto different numbers of resources. So if you move this application to a different system, elastic computing will automatically optimize the code for that system. If you add more resources to your current system, for example, say you add another GPU, well, the elastic computing framework will automatically start using that GPU by choosing different implementations, different parallelizations, and so on. Again, all without any changes to the application code. And finally, elastic computing is also adaptive because it can adjust its implementations to changes in input parameters. For example, we may call a sorting function at the beginning of our application that sorts 100 numbers, in which case elastic computing may select a quick sort implementation. But later on, we may only sort 5 numbers in a different location, in which case elastic computing could select an insertion sort implementation. Okay, so how does this elastic computing framework work? There's basically 2 main steps for determining how to efficiently execute any elastic function. The first step is what we call implementation assessment. And this is basically responsible for predicting the performance of every implementation option on every system resource. And the second step is what we call optimization planning. And what this does is basically it analyzes the predicted performances and performs a huge design space exploration in order to determine an efficient execution decision, or in other words, an effective plan for executing a function for any runtime condition. So for any input size, for any number of resources, for any type of resource, optimization planning is going to create a plan for that situation. And as you can probably guess, these 2 steps can be quite time consuming. So to avoid, a huge runtime overhead, we instead basically execute these 2 tools statically at what we call installation time. So the way this works is that you install an elastic function into the framework, at which point it will perform these 2 steps and output a set of plans. And then at runtime, when an application calls the function, there are function execution tools that will simply, analyze the optimization plans and basically just perform a simple lookup into a data structure to figure out what is the best plan for the current runtime conditions. And by doing this, we can basically, minimize the runtime overhead, making it, insignificant in many situations. All right, so let's take a more detailed look at implementation assessment. And again, this is responsible for predicting the performance of every implementation of an elastic function. Now, this sounds a lot like, the huge amount of work that's been done in performance prediction, but what makes implementation assessment more difficult is that it has to predict the performance of every implementation for all possible input parameters on every type of resource in a system. So it's a very difficult problem. And then the output of implementation assessment is what we call an implementation performance graph. And this essentially just represents the estimated execution time across all input parameters on a single resource for the corresponding implementation. To give you a quick example, the bottom of the slide, shows, some quick sort C code. This would be run through implementation assessment, and it would output, this IPG, which shows the estimated performance. And then, what this enables then is, other parts of the framework. So if something calls, a quick sort implementation, or, if the optimization planning tools are considering a quick sort, and it knows that the input size is 10,000, it can simply do a lookup in this, IPG to figure out the estimated execution time of that implementation. So I won't go into the details right now of, how we generate this IPG, but the basic idea is we sample different input sizes, measure the actual execution time on each resource, and then basically interpolate between those samples in such a way that we try to meet a desired accuracy. So after implementation assessment, the framework then performs optimization planning, which basically analyzes these IPGs in order to determine, or predetermine efficient implementations for different situations that can be stored as a set of plans used by the function execution tools when the function gets called at runtime. So optimization planning it does a lot of things, but it basically answers two main questions for, how to execute a function. The first question is, which implementation is the most efficient for a given invocation? There's an example of this shown at the bottom. So there's an IPG for a quicksort implementation and an IPG for a bitonic sort implementation. And so basically the optimization planning tools can figure out the best implementation for different input sizes by just analyzing these IPGs and seeing which one has the lowest execution time at each input size. So another question that optimization planning has to answer is how to efficiently partition the computation or partition the inputs across multiple resources. So this is where the load balancing comes in, and I won't go over the details here, but you can read about them in our papers. So finally, just to kind of give you the big picture of how everything ties together. So with elastic computing, the application designer, from their point of view, they basically write code the way they normally would. They write some application code using potentially any language, C++, Java. They compile that code into an executable, and then they run that on whatever system they're targeting. So the difference is, again, part of their application uses some elastic functions, so they have to, the only real change they have to make to their code is that they have to call these elastic functions instead of just writing arbitrary code. And then when these functions get invoked at runtime, the elastic function execution tools will analyze the predetermined optimization plans and find a way of maximizing performance. However, one question that has not been addressed so far is where do these elastic function implementations and where does this knowledge base of information come from? So for every elastic function, there basically has to be some designer that creates that elastic function. And there's different use cases that we envision working, but there's three common situations that we can see. One would be basically the implementations provided with an elastic function could come from hardware vendors. So NVIDIA could provide highly optimized implementations of common functions. Likewise for an FPGA, Xilinx and Altera could provide pre-designed cores that correspond to a given elastic function. Or there could even be, open source efforts where, just anyone can contribute, a new algorithm or a new optimization or a new parallelization strategy to an existing elastic function or a set of elastic functions. And then once these functions have been created, they get compiled just like, any other function would be. They get passed through the framework so that the framework, does the implementation assessment, it does the optimization planning, and then creates, the set of, strategies to use. And when you put this all together, you end up with this, this runtime optimization approach where designers simply call functions, and then the elastic computing framework dynamically figures out, how to optimize it and how to parallelize it across resources, giving you significant speedups without, any increase in application design complexity. So there's more detailed experiments in our papers, but I wanted to give a quick overview of, one interesting example of elastic computing. So what we did here was we evaluated convolution, an elastic function for convolution, on a system that had it was basically a quad-core microprocessor. It was a Core i7 that had 3 GPUs and an FPGA attached to it over PCI Express. And so for this elastic function, we manually created 5 different implementations. We basically created some time domain implementations, some frequency domain implementations for each type of device. and then we added a parallelization strategy based on overlap add partitioning. So the chart on the top left shows how the speed up of elastic computing basically increased as we made more and more resources available to the framework. And as you can see, when we ran this on only the CPUs, we basically, got a particular performance which wasn't very good. When we added a GPU, the elastic computing framework automatically, sped everything up and achieved a speed up of around 30x compared to the CPU implementation. If we added 2 GPUs, we got a speed up of, just under 50x. If we considered only the FPGA, we got a speed up of around 50x. If we looked at all 3 GPUs, we had a speed up of around 60x. And if we continue to add more and more resources, we get up to a point where we have a speed up of about 80x, which again was achieved completely transparently without any changes to the code. The application designer simply called this convolution elastic function. And on the right side, it just shows one example of how the work was partitioned across devices. So initially, the input was, went through this parallelization strategy of overlap add partitioning, and it broke up the input into basically 2 sets. One of those sets was then processed on an FPGA using a frequency domain implementation. The other set of data was partitioned again into 2 subsets, and each one of those was executed on a GPU using a time domain implementation. So these aren't necessarily the best implementations because we didn't create a frequency domain implementation for the GPU or a time domain implementation for the FPGA. But this is just meant to illustrate that, given some knowledge base of implementations, elastic computing was able to automatically parallelize and choose appropriate implementations for each device. So just to summarize, there's been this trend towards multi-core heterogeneous architectures, which, achieve very good performance and very good energy efficiency, but are very difficult to program. Elastic computing's goal is to address this problem so that basically mainstream designers can take full advantage of these performance benefits. And it does so by providing an optimization framework that dynamically optimizes functions or specialized elastic functions from a function library for potentially any system. It essentially allows a designer to specify what they want their application to do without specifying the low-level details of how. So if you're looking for more information, you can see my website. We have a number of publications on this topic, although I should warn you, they don't all have elastic computing in the title. We've basically written a paper on each step of elastic computing. You should still be able to find them, but if you have questions, you can feel free to send me an email. And if you have, any interesting ideas or applications where elastic computing may be beneficial, feel free to contact me. Thank you for your time.